So, hello everyone, and today we're going to talk about how we serialize data in Yandex. And more specifically, we need to talk about the motivation behind yet another approach for data serialization, but about the key ideas which helps us achieve what we consider our goals, discuss in more details the serialization algorithms used, discuss the standard containers and interferes with our approach, and talk about efficiency a little bit. So the first question, which probably have crossed your mind when you heard about yet another serialization technique, is something like, why on earth should they need another one? Haven't people done enough of them, right? Well, it's kind of a good question, and to answer it, I need to tell you a few words about who we are and what our specific demands are. So I work at Yandex. For those of you who is unaware of this company, it can be thought of a Russian Google's leading internet portal and search engine in Russia. And specifically, I work at Yandex Maps team, providing our users all kinds of geo-informational web services they should ever need. This includes city maps, it includes driving directions, real-time traffic conditions, public transportation vehicles, etc. And in order to do all this, we need to deal with huge amounts of data. And concerning these amounts, well, our huge amounts are, well, huge. It can be up to 100 gigabytes, and usually some dozens of gigabytes in size. We'll consider what size would require to fit the whole road graph for the whole Earth, for example, for driving directions. Our data are basically generated, disseminated, and used cycle. So it was some sort of content manager that pushed the buttons, and the data is accumulated from sources of all possible sorts, well, mailed, distilled, and finally some sort of, well, road graph is produced, then distributed to the other machines which use this sort of data to handle user requests. And the data are generated relatively rare. So the graph may be updated on a weekly basis. This model for public transportation prediction things is updated on some sort of weekly basis as well. And even the real-time traffic conditions, which updates once in a couple of minutes, can be considered relatively rare compared to how often the data are used. So the usual load on our servers is something like several thousand requests per second. So the vast majority of our data access is read-only. And due to large amounts of data, reading them becomes an issue. So you may imagine how long it will take to parse and read all the zillions of, well, vertices and edges of our road graph. It can take us dozens of seconds, and that basically means dozens of seconds of downtime of our service. And we're particularly not happy with that. Of course, we could invent some tricky approaches like, well, loading the data in the background while still handling user requests with the old version of the data, or the old version with the code should we consider software upgrades. But what we want to do is to try a fundamentally different approach. We want to invent the way to serialize the data in such a way that the read time is reduced to the maximum extent ever possible. More specifically, we want the read time to be all one with respect of the size of the data being deserialized. Well, quite challenging task, isn't it? So in order to make this possible, we're going to consider a few perhaps useful thoughts. First, when we talk about data reading, we're actually referencing two kind of independent operations. First, we need to physically move the data from the disk when the data resides into the memory where it can be worked with. And the second, we need to decode the data from the format in which the data lie on the disk into the format convenient to work with. And these two steps can be considered independently of one another. So the first one can be dealt with since we recollect that the modern computers have a thing called disk cache, which is likely to store the data accessed recently. And if we use a memory map for bringing the data to the address space of our process, then the data used before, previous version of the data used for handling requests, or the current version of when we talking about software change, is likely to be used recently and thus are likely to be in the disk cache. So, and if our new data arrives, they usually arrive in some sort of network, read by user process and then written to the disk, so they are also likely to be there in the disk cache. And so, if we just use an mmap operation, chances are that the data will be instantly brought to the address space of our process in our own O1 time. So the only operation we need to deal with is to deserialize them, to transfer them from the format they are on the disk to the format they are in the memory. So what is the usual serialization it looks like? Let's consider this very simple structure. Struct person, having first name, having last name, having an age. The first two are strings, the second is the integer, and every single serialization algorithm, be it Boost Archive, be it Google Protocol Buffers, be it, well, perhaps something else, will handle this in a very similar way. First, it serializes the first name, then it serializes the last name, and last, it serializes the age. And first name and last name as strings can be arbitrarily long in size. So how things are usually done? First, we write the size of the string, then we write the bytes of the string. So 4 bytes, then 4 bytes name is well, John, and 5 bytes of data, then we write in age, and we're done. So this is pretty simple to implement, simple to understand, and even simply to read back into the memory. Well, you need to read back this kind of serialized structure. First, we read number 4, then we read 4 bytes placed in the first name, then we read number 5, then we read 5 bytes placed in the last name, then we read an age, and we're done. But in memory, things are laid out quite differently. There's something like this. We have a first name, we have a last name, they're strings, basically consisting of a pointer to the data and the size of the data, and the pointer points somewhere else. So when you have a look at this picture, you can see the data can be naturally subdivided into 2 parts. Well, there may be not too good choice of the words, but still. The actual data, which can be arbitrarily long in size, and header which references the data. So this thing I want to repeat once again. So the actual data is there in the heap, doesn't have to have any predefined layout and size, and usually contains most real data. And the header part, which are usually some sort of memory member variables, referencing the data in the heap and having predefined layout and predefined size known at the time of the compilation. So if we want to avoid wasting time decoding, we must reconstruct the same layout when laying out bytes in our file. So everything in our serialized file should be subdivided into those 2 parts as well. So we need to write things twice. First, we need to write the real data. And second, we need to write the header part referencing that data. So when we're talking about something referencing something else, another problem emerges, how we're going to store the pointers. When we talk about something allocated with the malloc or operator new or whatever else, we know the absolute address of the memory, so we can just store it and be happy with that. But this is no longer an option when we talk about memory mapped files, since we're not knowing where exactly the file is going to be mapped. So we have to store relative addresses, offsets. The most naive approach, the first that ever comes through your mind, is perhaps store offsets relative to the beginning of the file. But it has a major downside. When we do referencing theme, we need to track this beginning and propagate it to every link being dereferenced. And this is kind of error prone. It doesn't play nice with familiar C++ interfaces we're trying to reconstruct. The more tricky approach is to store offsets relative to the position of the offset itself. There's something like this. When we need to store this capital letter J, we just count displacement. This J is kind of 11 bytes ahead of this pointer, so we write just minus 11. The same thing applies to this capital S. Well, assuming this pointer and this integer is 4 bytes in size, so the S is 14 bytes ahead, so we write minus 14. This way, on the one hand, data aren't bound to any specific memory locations. They're relocatable, they can be brought anywhere, and provided these displacements don't change, we can easily dereference things. But on the other hand, we don't need anything to dereference a pointer besides the pointer itself. We just take the address of the pointer, shift it by whatever the pointer contains, and get away with the real pointer, the real data. And having all that said, we can try to reconstruct a class behaving like a well-known standard string, taking, well, these -11 and 4. It can be done with something like this. Well, here's our offset, here's our size, here's our two public member functions, data and size. Data just do whatever I just told, takes the position of the pointer, shifted by whatever contains in the pointer, and returns as the position of the real data, and size just return whatever stored in the size. And having the data and the size, we can reconstruct the begin and end, and having those, we can do a whole part of real read-only interface of a standard string. Well, comparisons, substrings, searches, whatever else. To make things even better, we don't need to construct this kind of string. We just pick a specific location in our memory mapped file, reinterpret, cast it to this class, and we have a string. And this string very closely resembles our familiar standard string we're all used to and we're all familiar and we all love. So we maybe try to propagate this approach to our user-defined structures. But there's where a kind of duplicity emerges. In order to write data, we need something to write. So we have to define, well, what I call struct W person to write, which consists of two standard strings which can be created and populated and then serialized. And in order to read and use them in a memory mapped file, we need another definition, maybe some struct R person, having very similar fields, but having slightly different types, namely our read-only string, which can be casted and then used. Well, C++ seems to have a feature that helps us to deal with this kind of duplicity, named templates. So we can establish two, well, tags. I call them standalone and mapped. And we can provide a template class string, aliasing a specific version of our string depending on what the tag is. This approach can be propagated to the user struct as well. So this struct person behaves exactly like the W person or the R person mentioned above, depending on what the tag is. So having all that said, we can do the following. We can create an instance of person of standalone and fill it out. Then we can serialize it into file in some way. Then this file can be, well, travel in space and time and on a different machine or whatever else, and can be memory mapped into memory, well. So we can reinterpret cast a specific position of our file back into struct person of mapped and be used with a very similar interface that was used when we were populating things. So the key concepts on the single slide. All data are naturally divided into two parts. The header part, which is a member variables of structs and classes, which have a specific layout predefined at the time of compilation, a specific size. And the data part consists in holding a real data, can be arbitrarily large, and are referenced by the headers. So we need to reconstruct the same approach when we write in data. First we write data, then we write headers. When we write pointers, we store them relative to the position of the pointers, and to avoid duplicity and to simplify data definitions, all our data are templates whose first parameter is the placement strategy either standalone or mapped. So having all that said, it seems like all magic can be incorporated in one specific function, namely write, which takes a standalone representation of our data and lays out bytes in the file it produces in a very specific manner. So we're going to discuss this serialization algorithm in, well, more detail. First of all, what can be serialized? No surprise, we can serialize plain old data. Then we can serialize user structures, provided we know how to handle member variables of the structures. And the last, we can serialize containers if we know how to handle the data the containers hold. This criteria is kind of recursive, so we can easily handle some complicated things like structures possessing a map of string to a vector of another structure possessing, well, whatever else. So when we talk about two passes of serialization, we basically talk about, well, two functions. First, we need a specific function to store the data. And then we talk about another function which stores the header. They need to exchange some sort of information, well, where the data exactly begins in the file. So it can use a temporary queue provided passed to them by, well, our framework as a kind of a scratch pad, so it has somewhere it can track the pointers in. And in order to save these pointers, we need a special kind of stream counting all bytes written and thus capable of providing us the offsets where we're trying to write at the moment. So these two functions need to be defined for every single type we're trying to serialize. So no surprise, they can be easily defined for plain old data. The write data is basically an op. It doesn't touch streams in any way, it doesn't touch queue, and it just does nothing. And write header is, well, pretty straightforward as well. It just takes the bytes consisting in our data type and writes them in the stream just the way the bytes are, not touching queue in any way once again. Concerning user-defined structures, we just call the write data recursively for all member variables, and we write in header, just calling write header recursively for all member variables, but paying attention to the alignment. We need to keep track that the compiler might introduce some invisible padding member variables to make sure the all memory access is aligned. And we need a struct introspection. Since C++ doesn't give us a way to traverse to the member variables of our structure, they have to do it by hand. So every single user-defined structure we are trying to serialize should expose their field via the special member function traverse fields, accepting some sort of a functional object and feeding with the member variables in the ordering they were defined. Well, this approach has its own pitfalls. When we require our users to specify the fields twice, first when they are defined and second when they are exposed, one might mix things and specify things on ordering. We can track this by requiring a field offsets to increase, and then we notice that offsets decrease, the particular offset decreases, then the user perhaps screw things up and we can raise an exception, trigger an assert, or whatever else. Things are kind of worse when user forgets to specify the field. In some circumstances, we might not be able to tell a missing field from a hidden field inserted by a compiler to ensure aligned memory access. So we just can't do anything. We're still waiting for, well, struct introspection could emerge something around C++ 22. There are some sort of proposals, but I feel kind of pessimistic that those proposals will find its way to C++ 17 since there's little time left. So that's basically all for the user-defined structures. And concerning the containers, each container is very special. So we just cannot come up with a generalized version of our write headers and write data suitable for handling every single container being supported. So serialization routines for each container supported needs to be written by hand. So what exactly the standard containers that we provide, that we support? We have already discussed a standard string, which is, well, pretty straightforward. It just references a bunch of bytes, so little trouble supporting a string, okay? Let's talk about something slightly more difficult, a vector. Usually a vector is stored, well, some sort of this. It stores all header part of its data in contiguous region, so it can easily reconstruct a pointer to arbitrary nth element of the vector by just multiplying this n by the size of t, shifting by the number, well, offset of beginning of this region and have a pointer to our nth element. So in order to provide random access, we need to reconstruct the same thing. So here basically our write data for our vector, which first writes the data part of all elements traversing each element, then and keep tracking of where the elements begin in a temporary queue. Then we traverse elements once again, writing header part of the element in contiguous regions, just like the standard vector does. And when it comes for formatting header, we just use the memorized location of the beginning of that contiguous region to write the pointer, to write the size, and be done with that. So if we have a vector of above-mentioned struct person having, well, 3 elements, we're going to end up with something like this. First, we have the bytes the strings consist of. Second, we have, well, the big mess, so arrows consist in our fixed header part of our structures. Well, these repeatable color patterns may indicate, well, the elements of the vector. And then we referencing the beginning of these elements and writing 3 at the size. And we're good. The standard library provides us with more sequential containers. Double-ended queue, linked list, single linked list, rope, whatever. All those elements, all those containers, differ in the way they handle insertions and erasures. But the read-only interface is, well, no better than the vectors, since the vector already provides us random access, and what can be even better than that. And we simply cannot change anything in our memory mapped file we're referencing in a read-only manner. So we don't need any of other sequential containers. We might need those to, well, populate things, but their memory mapped counterparts are essentially aliases to the one the vector provides. So this is basically it with the sequential containers. What about the associative ones? Well, our map or set or whatever else usually provides 3 operations. It can search element in logarithmic type, it can insert an element in logarithmic time, and it can erase an element, like again, in logarithmic time. And like we said before, we're not interested in insertions or erasures, so the only operation left is search in O log n. And there is a simple data structure which allows us to do searches in logarithmic times, namely sorted vector and a binary search. So we don't have to reconstruct all those balanced tree things. We just have to traverse elements in our map or set as if it was a vector and stored in the contiguous region of memory. So we're done with the map and the set, and here comes unordered versions. They're kind of tricky. We're not happy with the vector. At last, we have to do something by hand. Well, usually unordered maps consist of maybe thought of a vector of vectors of elements. Those vectors are buckets, and, well, it's pretty straightforward routine for finding an element. We compute the hash. We use the hash to find out the bucket. We traverse the bucket to find out where our element is, and we return it. But this approach has its downsides. First, storing that many vectors introduces lots of additional overhead. Second, implementing, traversing elements from beginning to the end of the whole unordered set can be tricky, since you have track interrogators to the outermost vector, to the innermost vector, that kind of things. So we can flatten things a little bit and store all elements in one contiguous region of memory and keep tracking of the buckets, storing pointers to the beginning and the size, the count of elements of the bucket. So our find routine changes just a little bit, and our iterators simplify dramatically, so it's just essentially iterators to the vector. And we can save a little more space by just recalling that the buckets are placed sequentially as well. So if we take a beginning of the bucket and shift it by the count of elements in the bucket, we end up with the beginning of the second bucket. So we don't have to store sizes. We just have to store the beginning of the buckets in our second vector. And when we need to find an element, we just as early we compute the hash, we find out the buckets where it is, we use this bucket as a beginning, and the beginning of this following as the end of ours, and we traverse the element in the range, and we're happy. So when we're trying to lay out the bytes, we begin by laying out our elements just like we did with the vector. But now we're noticing where our buckets beginning and where are ending, and use this information to reconstruct this array of offsets representing boundaries of our buckets, and just write offset and bucket count like we did earlier. So here's basically kind of outdated slide. Okay, missed them. Our approach has its own downsides. First, it doesn't have any incremental writes. In order to serialize thing, we need to have the whole thing in our memory ready to be serialized. This can be a problem if our data grows, well, huge. The second, it completely lacks extensibility. If we talk about Google protocol buffers, well, they essentially a map of field ID to the field contents, so one can easily add new member variables, add new fields, as well as keep their ID unique. And we don't have space to place any extra fields, any extra member variables. So all definitions of all our structures should be the same through all binaries that share their data, that use the data that generate it. So migrating from one data format to another might be a challenging task. One needs to synchronously update all those code that generates the data, that uses the data, and the old data being serialized between the two. And last, the serialized data are bound to a specific architecture. It relies heavily on the endian, on the word size, of the integer size, alignment details, that kind of things. So if you need to provide, serialized data to be read in 4 different architecture, you perhaps will end up having 4 different versions of your file. Oh, another downside is when we're fooled, when we're given a wrong data, there is little can we do to do any kind of safety checks, since we're just reinterpret and cast the specific memory locations and try to dereference them as if they were pointers. So if we're given some sort of junk, we'll most probably end up with a segmentation fault. Well, it turns out we can establish a kind of a safety net by just computing, data version. It's some integer number calculated using the following scheme. For plain old data, we just hash, type ID, type name of this data. For user-defined structures, we just mix versions of all its member variables. And for containers, we just hash container type and the version of the data the container holds. We need to tell that we don't have to traverse the elements of the container in order to compute this data version. So this data version calculation is a one operation with respect to the size of data being serialized. So we can store this data version along with the file we create when we're serializing data. And with the reading it, we calculate the data version once again and compare it to the one being stored. And if we when we notice a mismatch, then we're probably fooled and the user probably wants us to crash. So we can notice that and trigger an exception, or raise an exception, trigger it, and assert or whatever else. So what's about the efficiency of the whole thing? So what we're measuring? First, I've generated a 5 million element matrix of 10 character strings. Then I serialized it, then I deserialized it, and then I traversed it in a random order. We're comparing our approach with the booster archive and with the Google protocol buffers. So more specifically, this is the definition of the protocol buffer thing. It lacks support for complicated C++ data structures. It provides only repeatable messages, so we have to incorporate it with the with the repeated messages in order to achieve our, well, structure. This is the boost variant, just a very simple thing. We can just hold a vector of vectors of strings and feed it to the boost archive things. And the same thing, our memory mapped approach, holding our, well, template definition of a vector and exposing it to the library. So, well, here are the numbers, what they're telling us. First and foremost, one can notice this big shiny 0. Just like we wanted, the data reading went completely off the instruments, which is, well, kind of cool. And on the other hand, when we compare the timings required for data traversal, it matched those of STL containers. It is slightly less, since all relatives, all pointers are relative, which causes an extra addition to the reference things, but still it can, well, less than 10%, I believe, right? And significantly outperform the Google protocol buffers. On the downside, serialization is 3 times slower. We're not particularly concerned with that since, like I told you at the beginning of the talk, we are doing serialization much less frequently than we're reading the data. So there's 3x performance down, performance decreases, well, pretty okay with us. And the serialized data is larger than both boost and protocol buffers, which is, once again, no surprising since we have to, well, respect the alignment. We can't use this fixed variable, fixed width integers, protocol buffers use, etc., but we still require less memory to operate this data, since we just can't use them in the way they are, while both boost and protocol buffer require the data to be read to the standard containers counterparts, and this can introduce additional overhead. In some specific circumstances, this overhead might be 10 times the size of original data being deserialized. So what we've got? We've got our serialization library, which allows us to manifest our data in plain old C++, we all know, we're all aware of. Doesn't require us any specific domain-specific language, any additional compiler tools, preprocessor, or anything else, which allows us to access our data with a familiar STL-like interface, which, the most important thing, allows us to completely eliminate data reading phase and the data reading step. So if our data happen to be there in this cache, we can just start accessing them instantly, and we can do this instant access with a speed almost as fast as those of STL containers. And the last, we have a good data locality, meaning no reallocation, data holding well tightly, meaning more cache hits, meaning less timings. What are possible use cases of this theme? If your data obeys the general generate, distribute, use cycle, so if you're writing the data almost as frequently as you read it, then you perhaps might be using some sort of database. But if you're generating data rarely and reading the data oftenly, you may consider this approach. When you have that much data, then reading them becomes an issue, and you don't want to waste time decoding them from one format to another. And while your data is well structured, there is simply no sense in storing one huge text file in one big standard string. It can be, a big address dictionary. It can be, auto-completion data. It can be dump of, Wikipedia for offline readers, whatever else. Well, in Yandex Maps these days, this approach is used for serialize nearly every data being processed, used for handling our user requests. So this is basically it. If you have any questions, I'll be happy to answer.
First of all, thank you for this great presentation. I want to understand and to ask you, maybe I didn't understand correctly, how are you dealing with the versioning of this serialization? Do you have this approach of versioning the serialization?
You're asking about data versioning?
Yes. Yes.
Okay, let me take to this once again. We use this data versioning to make sure that the data definition used when we're generating the data match our own definition that we expect to have, we expect our data to have. So we just take, well, the simple thing. When we have just an integer, the version of the integer is basically a hash of, well, int. When we have a user-defined structure, we just traverse through the fields of member variables of our structure, injecting the version of each member variable polynomically, and thus making the version of our structure. So it can be, well, boost polynomial hash, hash combine, hash combine, hash combine, hash finished. And when we talk about containers, we just use a type of a container and the data version of the container. We combine it into once again, hash, which represents us the data version of the file of our data being processed. So if we, well, add another field to another structure, this version is most likely to be changed, and we will notice then we're trying to deal with the data. So it can protect us from trying to misinterpret the data, which if we tried to, well, to reference what we think the pointers are, so we won't end up in a segmentation fault. That's basically the purpose.
Okay, thank you.
Hi, just wondering, does your benchmark change a lot with the size of the strings? Because you said you use 10 characters, right? And if you use larger strings, does that change a lot, or?
Well, I didn't measure different string sizes, but I can estimate that, well, there could be a little minor changes, perhaps, which will perhaps increase this boost and protocol buffers things even further, since they have to move the bytes from one portion of memory to another, which we don't have to do. So, well, if there are less data, there are less things to handle. But this is just estimation. I didn't carry out the measurement.
Just a detail. As far as I know, the STD string for 16 characters, or it's implemented by char array. After that, it's about allocation. So maybe your benchmark, it depends, it's changed a lot if you are using a longer...
It's a recent implementation of standard strain, which allows us short strain optimization thing. And we were using the former one, which used implicitly shared strain, which doesn't have that thing, which did the allocation for every single strain being constructed.
I have a question too. If I understand correctly, you first write the, say, dynamically sized data, the actual string characters, and then the headers of that. So if you read back, you somehow need some point to jump in and discover the headers. Do I get this right?
Well, if you just write an arbitrary data, then yes, you have to track the pointers. We have to store it elsewhere. But if we're just writing a single huge structure, containing some sort of containers and some sort of whatever else, then, since we're writing the varying size part first and the fixed size part last, and we can just point to the end of the memory region, shift it back by the size of our structure, and get a pointer to the beginning of fixed size structures. We can reinterpret cast back to the type we need.
You could have reduced the size of the string by removing the 0 byte, I guess. You have a string view.
I surely could, but this will cost us eliminate a C_str method of our string, which we're not happy doing.
Well, you could just have a toString from your arrow string.
It costs us additional memory copy. We're not happy with that. We want to be able to pass this memory map string with all sort of str, str, whatever else, without any need to decode the thing in every possible manner. And appending this Trojan 0 is just another way of decoding data. We're not happy with that.
You're right that your approach is about 3 times slower, but you're writing 3 times as much data.
Sorry?
You wrote on the slide that it's about 3 times slower, but you're writing 3 times as much data. So have you cleaned the data for disk access, for instance? So are you actually, is it generation time to write, to generate the serialization data? Is it disk access time which you're seeing in the here? I would think that it was disk access and not.
We writing to the disk sequentially. We don't do any disk seeks, so the disk access usually is not a concern. So the operating system has all sorts of disk buffer, write buffers, and all kind of things. This 3x performance penalty is the most can be explained by the amount of passes we have to do to write the data. We write the data first, we traverse the whole data first to write this, variant part, then we traverse the whole data once again to write the fixed part, and we need to track those pointers between the two. It all costs us additional CPU resources. It basically, I believe has nothing to do with the disk performance.
Is it possible to write in any kind of multi-threaded way, or would you just have to write several files, one file from each thread?
Sorry?
Multi-threading, parallel. Is it possible to do parallel writes, or would you have to have one output file for each thread if you're writing?
Well, I personally didn't consider all sort of parallel writes, since this will surely overcomplicate things. And like I told before, the writing performance penalty was not an issue particularly for ourselves. So I just didn't think in that way. And multi-threaded reading is not an issue since the data are modified. So no problem, could merge. Sorry, please wait for the mic.
Sorry. Do you do something to preserve the consistency of the file? I mean, if the computer crashes when you're in the middle of writing, then some pages are saved on the disk and some are not.
Are you talking about serialization or reading?
Serialization, because then you get problems when you're reading it back.
Well, when you're serializing data, you're just using a usual safety net of writing temporary file, and after you are done writing temporary file, automatically replace the old version with the new version. And it's beyond the scope of the library itself. It's some sort of control script that drive the data generation process. So when we serialize data, we're not concerned being interrupted in the middle. This is something which our external software has to deal with. Anybody else? No questions, I believe. So then, thank you everyone for your attention.